Good morning, everyone. Welcome to another episode of KTPI's seminar series. So there are other audience who are not KTPI members also. So I will briefly introduce you what is KTPI. Of course, KTPI is an acronym. It is an acronym for Kerala Theoretical Physics Initiative. It's a vibrant community. It's an emerging community that aims to reshape how we approach the physics education and physics research in Kerala. So KTPI represents something truly special. It's a global network of physicists who shares common vision and a root in Kerala. So our include faculties, PhD students, and postdoctoral fellows across the globe. We united by our passion towards the theoretical physics. So what makes KTPI unique is that we are planning to nurture next generation physicists right here in Kerala. So we believe that I hope the excellence should not be confined to some selected institution. It should flourish where the curious mind gathers. That's why we are working on the basics of postgraduate physics education system. So one of the flagship program we are hosting nowadays is called Active Research Training Program. So which helps which catalyze our mission. So it's a 2-year program where uh, we pay as motivated postgraduate students with KTPI members who act like a project mentors, and they will take a research problem and they will work on it for 2 years. And we hope for a research output out of that project, and these students can be take that project as their master thesis. So we have been successfully running this program for past few years, and it's very successful program. In addition to that, we also provide them with some essential research skills like basic research tools so that they are also equipped not just with the knowledge, but also the tools to create new knowledge. So welcome all, and even our guests also welcome to KTPI. So here we celebrate physics. So today our speaker is Dr. Anurag Priya Saha. So Anurag did his bachelor's from Presidency College back in 2012. Then he did his integrated PhD from IMSc right after his bachelor's. Then he worked on, I think, soft graviton theorems in higher dimensional spacetime with Professor Alok Lata. So then he did a couple of postdoctoral positions, mainly right after his PhD, he joined HRI, and then he also acted as a postdoctoral fellow in IISc Bhopal. Then he joined an Indian Institute of Science as a Inspire faculty fellow. So now today he's going to talk about a new representation of scattering amplitudes um, in string amplitudes today. So he's also talking about one of his serendipity of representing the pi in a new series. Hopefully he will also sell that in a convenient banner. And I also encourage young students to ask not just the confusion regarding the talk, but you can also ask your confusion in the direction of string and theoretical physics directions also. I hope it's fine with you, Anurag. So over to you, Anurag. The stage is yours.
Yeah, thank you very much, Jishnu, for the kind introductions and also inviting me to this platform. I really appreciate this endeavor to outreach science among students and other people. I hope there are more such initiatives in our country. So, okay, so let me start the, with my talk today. So today I'll talk about this new representations of string amplitudes. And this is something that we have been thinking for past couple of years, almost couple of years. And this talk will be primarily based on these two papers that are already out. And these papers are written with Professor Arnab Sinha, who is a faculty member at CHEP IISc, and also along with two graduate students, Faizan and Debapriya. Faizan will be graduating soon. He'll be going to INF in Genoa for his postdoc, and Debapriya is a senior graduate student. So before I go to the main part of my talk, let me give a brief overview of what my work is about. And my work is mainly about scattering amplitudes. So I'll assume some familiarity with quantum field theory among the audience. So if I understand the audience might be quite diverse, and if there are some confusions or some questions, please feel free to ask at any time. So, first of all, what is scattering? So, scattering in physics is the study of collision process. And by collision, what I mean is the following. This is something that we are quite familiar in our day-to-day life. Like whenever some bodies they collide, they scatter off, and we are interested in understanding these kind of phenomena. So let us assume in a simplistic setup that a bunch of particles are coming from far past where they are not interacting, they are not talking to each other. And they come at some point in space-time, they interact, they collide, some processes happen, and after the interactions are over, then they again fly off to far future at infinity. So what we are interested in understanding the processes that are happening when they are interacting among themselves in some restricted uh, region of space and time. And why is scattering interesting is because scattering describes a wide range of natural phenomena, meaning almost all the natural phenomena can be described using this scattering process. For example, we can ask, why is the sky blue in color? That's also a scattering phenomena. The light comes, and the photons, they are scattered in the atmosphere. There are several processes, and it's accumulation of various physical phenomena that lead us to see the blue color of the sky. And similarly, we can try to describe Newton's laws of gravitation and corrections beyond the Newtonian potentials that are coming from general theory of relativity by studying some scattering. So let's say Earth and Moon as a body, they are exchanging gravitons. So we can consider it as a two-body problem, 2-to-2 scattering, where there are like two massive bodies, they are exchanging some gravitons, and we can evaluate the Newtonian potential, which is basically given by G capital M small m by R, and its corrections of order G square beyond that, using these S matrix or scattering amplitude techniques. And in recent years, uh, over a decade, in a period of over a decade, there have been exciting studies about gravitational waves. And here, this is a snapshot of the gravitational waveforms that observations have experimentally verified. These gravitational waves which come out from binary black hole mergers. So it's the process where black holes, they are spiraling around each other, and finally they merge, and at the end they emit a lot of gravitational waves. And this is the template of this gravitational waveform. And this process can also be described using the methods of scattering amplitudes. So in particle physics, scattering amplitudes are very crucial in understanding the building blocks of the particles. So, and these building blocks are the tiniest constituent members that make our universe. Like uh, the physical laws that govern the subatomic particles. So those can be understood by studying the various scattering process. And these scattering experiments, for example, we are familiar with collider physics. Like there are collider experiments happening like all over across the world, starting from LHC to many other different places. What they do is probe the internal structure of the particles by smashing the particles. So they smash the particles, they eject the particles at a very high energy. The particles come together, they interact vigorously, and in that process, we learn about the tiniest details of the particles. So starting from the discovery of nucleus by Rutherford in the early 20th century to the discovery of Higgs boson at Large Hadron Collider over a decade back, scattering experiments have played very crucial role in understanding of the quantum world. And now we can claim that we have fairly a good amount of understanding about the standard model and all the elementary particles that build up the standard models. Now we know that standard models consist of something called hadrons. Hadrons are formed of these quarks, and then there are leptons like electrons, muons, and so on. And we also know about the force carriers like photons, gluons, or gravitons, although gravitons are not directly part of the standard models, but we believe they are there. And also we know about the weak interactions, the force carriers of the weak interactions like W and Z bosons. And the latest discovery was about the Higgs boson, which was experimentally verified at LHC. So all these elements that form the standard models to uh, to understand how they interact together, what we do is we use scattering amplitudes, and in one framework, what we can write down something called Lagrangian. I hope that this is not. I mean, if this is visible, like we don't have to go to the all the details of the each and every term, but this is a Lagrangian that encodes all the information about the interactions of these elementary particles. And there are like hundreds of terms in the Lagrangian, meaning there are like lot of interactions, possible interactions happening inside the standard model, like with these elementary particles. And we are interested in understanding these phenomena. So what do we study in scattering? So that's a question. Like what kind of measurements we do when we say that we are studying scattering amplitudes or scattering processes. Now there are varied range of physical quantities that we can measure. For example, we can measure the cross section. Cross section actually refers to as the probability of the particles that are observed in the scattering process. Then we can also measure the decay width, meaning every particle, like the physical particles, they have some finite decay width, meaning they decay given a time range. After a time range, they will decay. And so in the S matrix or the scattering processes, we can also measure the decay width, like how long that particle will survive. Some particles have actually very large decay width, meaning I mean they disappear very quickly, and some particles they live for a longer time. Then we can also measure the deflection angle, like when particles hit a particle and they change their trajectory. They don't go in the straight line, but there will be an angular shift in their trajectory, and that is referred to as the deflection length. And then we can also measure uh, quantities like correlation lengths, magnetic susceptibility, transport phenomena. These are very interesting as far as the condensed matter physics is concerned. We can learn a lot about the condensed matter system in this S matrix framework. So, like under one panel, we can say that scattering amplitude is a study of S matrix elements, and in fact, S matrix elements provide all the information about all these quantities. Now, usually, at least for the purpose of my talk, I will only refer to the perturbative calculation of scattering amplitudes. By perturbative, I mean there is an expansion parameter. And this expansion parameter is actually given by the strength of the interactions, which are referred to as coupling constants. So usually, the coupling constants are very small, like they are like as order of magnitude wise, they are very small in number, and therefore we can make an expansion in order by order of that coupling constant. And that is what is referred to as perturbative calculation. And there is a systematic way of organizing this perturbative calculation using some diagram or diagrammatic rules, which capture information about the kind of interactions that are happening and various other things. And these diagrams are usually referred to as Feynman diagrams. And here are some prototypical examples of Feynman diagrams. So this funny looking diagram actually appears in the study of quark scatterings. And these diagrams appear in the study of this gravitational potential, computational gravitational potential in 2 processes. And these give corrections to the Newtonian potentials. So we have general relativity corrections, which can be expanded in order of g Newton, which is the gravitational constant. And these diagrams come into play in that studies. So let us now see some concrete examples. At least one simplest example is a 4-point scattering. Now, 4-point scattering can be, so here is a diagram. Here what we consider is two particles coming, they interact, and then after the process, scattering process, or after they interact, they again fly apart. So two particles are coming with two initial momenta, P and K, and then the outgoing particles, let's say they have the momenta P prime and K prime. So there will be an overall momentum conservation, P plus K minus P prime minus K prime equal to 0. And to describe the scattering amplitudes, we require some invariant quantities. The question is, what are the invariants of? They are invariants of the isometric group of the space-time. For example, if we consider the space-time flat, that is Minkowski space-time, and that is the most frequent assumptions that we make in the calculations of this S-matrix. We do not have much idea about computing S-matrix in general curved background. So we'll restrict to Minkowski space. And that is what like all the experiments are related to. So we can describe the scattering amplitudes in terms of some invariant quantities. So these are called Lorentz invariant quantities. And it so happens that in a 4-point scattering, we can talk about these three invariant quantities, S, T, and U. And they are actually some combinations or some functions of the momenta. For example, S here is given by this quantity, P plus K whole square with a minus sign. And like if we go to the center of mass and center of mass frame of the two initial particles, then this just becomes the center of mass energy. S becomes center of mass energy. Whereas this T, which is P minus P prime, that means what is the energy exchanged between the particles, like between the initial and outgoing state of the particle in the scattering process. So this is also referred to as exchanged momenta of the particle, of the momenta that is exchanged between the particles. And U is another invariant quantity like this. And because of this momentum conservation, as I talked before, so there is a constraining relation between these three quantities, S, T, and U. And this satisfies a linear constraint of this form, S plus T plus U equal to 0. And therefore, we do not require all the three quantities, S, T, U, to describe the 4-point amplitudes. In fact, it is sufficient if we just consider S and T or any two variables to denote any scattering process. So now let us consider a particular scenario where we are looking at interactions between an electron and photon. So this is this scattering process goes by the name of Compton scattering, where in the initial stage we have electron, photon, and in the outgoing stage we'll again have electron and photon. And then there will be exchanges between like some states will be exchanged in this scattering process that we'll see here. So in order to describe this scattering process, what we can do is we can start from this Lagrangian framework where we write down these Lagrangian involving the photon, and these size they represent the electrons, and so there are these interaction terms here. Now, like if someone who is not familiar with this Lagrangian, especially the junior members, if someone who has not seen this Lagrangian, they might be able to recognize these set of equations. This set of 4 equations which um, describe the electrodynamics. So E and B are the electric and magnetic components of electromagnetism, and rho J, those are the like charges. Rho refers to as electric charge density, and J is the current. And these set of 4 equations that describe the entire electrodynamics. And this Lagrangian is a way of repackaging these equations under one framework. So given this Lagrangian, one will be able to derive all these equations of electrodynamics. And therefore, it is more convenient to use this Lagrangian in the quantum field theory framework to do calculations, especially to understand the scattering processes. And in this case, again, I repeat, we are interested in computing these S matrix elements or these scattering processes, which is an electron and a photon interacting. And in the final state, we again have an electron and photon. So we want to compute the S matrix elements for this process. And at the tree level, that is the leading order in perturbation theory, we will have these 2 diagrams. So these diagrams are a schematic and pictorial way of representing the scattering processes. So here, what we can see, these blue lines, they refer to, they denote the electrons, and this curvy red line, these refers to photons. So an electron and a photon comes, and an electron gets exchanged, and finally again that splits into an electron and a photon. And we can write down these 2 diagrams like this, and corresponding to each diagram, we can write down its corresponding S matrix elements, which has been written here. So now this one is called the S channel, because like here, if we label the particles 1, 2, 3, 4, we'll see that 1 and 2 are coming in this diagram, whereas in this case 1 and 3 are coming together, and this is referred to as T channel exchange. So what we see, like if we forget about all the technical details about all the terms, what we see is that we have terms in the denominator which are like S minus m square and U minus m square. So what do these terms represent? They represent, like if we have a function like 1 by x. So this function actually diverges when x goes to 0. So we say that there is a simple pole at x equal to 0 for this function. And here also, the same thing is happening. We have simple poles in s variable. Like whenever s is equal to m square, we have a pole, and this function diverges. Similarly, this function here, this has a pole when u equal to m square. And remember, s and u or t, these are kinematic variables, and they they are chosen like as per the experimental setup. So S and T and U, they are variables, and depending on what energies we are throwing in the particles, what energies, so S, T, and U will take that values. So if you are an experimentalist, what you would note down is for various values of S, T, and U, how the functions are behaving, and that will give like an idea or the framework of computing the cross sections. So in this case, what we see is that at the tree level, we require these 2 diagrams to compute the S matrix elements, and each diagram has a pole either in the S variable or in the U variable. And the reason I'm saying is that this is a general feature of scattering amplitude, meaning we encounter some kind of singularities in these variables. And I probably have forgotten to say, these variables are called Mandelstam variables. So scattering amplitudes have some singularities in the Mandelstam variables, and this is a general feature of scattering amplitudes. So now we can ask, what are the basic properties that an S matrix element should satisfy? And here are some list of properties. Although this list is not completely exhaustive, there are other properties, but these are the main or key features of scattering amplitudes. For example, locality. By locality, what we mean is that interactions are localized in some restricted region of space and time. So, for example, in these diagrams, what you can see that the interaction is happening at this point of space-time, and another interaction is happening here. So, and that is what we mean by locality. Then the scattering amplitudes also have analyticity properties in the Mandelstam variables, like scattering amplitudes will be some functions of S, T, and U, except some singularities. These singularities actually refer to some kind of resonances, or physically they mean there are some particles which are exchanged. So apart from those singularities, scattering amplitudes will be analytic in these three variables, S, T, and U, for a 4-point function. And another important property is the crossing symmetry. That means if we have poles in one channel, then the scattering amplitude will have poles or the singularities in the other channel as well. For example, here what we saw is this scattering has a pole in S channel, and therefore by crossing symmetry it should also have a pole in the other variable, that is U variable. And in general, the singularity structures are more exotic. Instead of simple poles, we can also have some branch cuts. And branch cuts meaning, for example, if we have function 1 by square root of 1 minus x squared. So then we know that there's a branch cut of x starting between -1 to +1. So along that line, the functions become singular. Okay. So schematically, this is a statement of crossing that given some singularities in one channel or poles in one channel, by crossing, we can also obtain information about singularities in the other channel. So here, this is what is referred to as S channel, and this is the T channel. And in general, amplitude will be given by sum of all such Feynman diagrams. Each Feynman diagram will have poles in one particular channel, and when we sum over them, we will get fully crossing symmetric function which have singularities or pole structures manifest in all the variables. So that is a general strategy of writing down scattering amplitudes. So now we ask, can we have a scattering amplitude which are given by only single channel expansion? By single channel expansion, what I mean is that can we have a process where only this diagram is there, and just by summing over diagrams of this form, that means the diagrams which contain poles in S channel, just by summing over those diagrams, can we obtain the full scattering amplitude? In other ways of phrasing the same question, can we can ask, can we have something like sum over S channel diagrams is equal to the sum over T channel diagrams, and each of them individual is equal to the full scattering amplitude. So that is the question we are posing here. So are there any questions so far? I'm happy to take questions if there are. Okay, so I guess not. So let me move on. So I hope the question is clear that usually in quantum field theory, we found, yes.
Hi, Arnab. So what is the motivation to think of one channel give you the full amplitude?
Right, a very good question. Thanks for that. So motivation, and as I'll explain later, this motivation actually gave rise to string theory. For example, here we are looking at some kind of diagrammatic expansions, and imagine that we have a kind of two-dimensional object where these diagrams are drawn, and then we can stretch these two-dimensional objects and deform this S channel to T channel, and then what our naive expectation will be that the answer produced by summing over these S channels will be also equal to the answers produced by summing over these channels when you stretch that two-dimensional, what is called world sheet. So that was the motivation, and also there were some experimental evidences. So earlier, people were looking at hadron scatterings. In hadron scatterings, like when they collected all this experimental data, they saw that hadron scatterings have certain kind of fall off behavior as we increase the center of mass energy. And because of that fall off behavior, what we can write down is express the full amplitude in terms of, let's say, S channel expansions, which will be equal to like expansions of this amplitude in terms of T channel expansions. These were 9 observational imprints or observed phenomena, and people are trying to explain those experimental data. And what they ended up is formulating so-called dual resonance model. So I'll talk about this in more detail. And this is one example of this dual resonance model, where we have, like, we can choose some particular functions where in some particular domains of the S and T variables, we can get the full function in terms of singularities of one variable. And that was the motivation of looking at dual resonance or single channel expansion amplitudes. So if this answer was not satisfactory, let me move on and I'll try to explain things in more detail. So as I was alluding to before, now let us imagine that we have a two-dimensional worldsheet description where we are drawing these Feynman diagrams. And from this two-dimensional perspective, what we see, like diagrammatically, of course, that this is S channel and this is T channel, but there is really not much difference between the S channel and T channel, because it is now drawn on some two-dimensional topology, where S channel.
Hi,
Yes.
Arnab. So maybe we don't know much about, or the audience might not be quite familiar with the world sheet. Maybe you can introduce what you mean by world sheet and all.
Exactly. Yeah. Let me introduce. Yeah, thanks. So by world sheet, I mean some kind of two-dimensional topology, and natural, like one world sheet thing that we already know of is a complex plane. So we have a two real dimensional, like a complex plane, which is two-dimensional. Two real dimensions it has, like x and y variables. So when I say z is equal to x plus iy, x is a real number, y is a real number. So it's a two-dimensional two real dimensional object, which is a one-dimensional complex plane. And we are drawing diagrams, or we are using that complex plane as some geometric object, auxiliary geometric space, and we are defining the scattering process in that or on that two-dimensional auxiliary geometric space. And this two-dimensional auxiliary geometric space is what we refer to as world sheet description. For example, look at this integral. So S and T here are the kinematic variables. And then we can write down an integral form integrating over these coordinates of the auxiliary geometric space, which is this z variable. And when we integrate over that, we obtain a function which is now purely a function of S and T variables. And now, if we look at it, we can immediately realize that this is a completely symmetric function of S and T variables. And in fact, this function, this ratio of the gamma functions, this is actually called Euler beta function. And this is meromorphic in the way that this has simple poles for positive integer values of S and T. A gamma function, gamma of x, has poles at negative integer values of x. Now, since there are minus signs here, so we will have poles at positive integer values of S and T. And there will be infinite number of poles. So here is a function which can be written as an integral representation over a two-dimensional manifold, which is a complex plane, in this way. And when you integrate over the coordinate of that complex plane, we get this function. So we will say that this is a two-dimensional object whose coordinates are z, and we are describing the scattering process as a mathematical function over the two-dimensional world sheet. Okay, and in fact, this function, was very important as far as history of string theory was concerned. In fact, Veneziano came up with this function. This in string theory describes something called tachyon amplitudes. Tachyons are unphysical particles because they move faster than the speed of light and have some bad properties. They are not really physical, but from the string theory point of view, these amplitudes do exist. And this was one of the first amplitudes written down in string theory, and this actually led to the development of string theory in later period. So this was written down back in 1960s, and then kind of revolution started for developing the string theory. So the point to emphasize is that so we have some objects which are described on the world sheet or a two-dimensional manifold, and when we do some operation on the two-dimensional manifold, we get some function which are functions of the usual kinematic variables. Now, as I said before, that this function, this is a nice example of scattering amplitude because this is symmetric in S and T. It has infinite number of poles, both in the S channel and T channel. And poles, for example, if we go back to these diagrams, so what do these poles correspond to? So we are saying that there's a pole at S equal to m squared. Now, when there's a pole, there are also exchanges. And this means that there is an exchange of electron. So electron has a mass m, and this the singularity in the S variable will be at m squared. That means over the poles, if we compute the residue, what we see is exchange of the electron. So every pole corresponds to exchange of some particles. And in this case, since there are infinite number of poles, so we see exchange of particles with higher spin. So in the earlier case, previous case, we had exchange of a spin half particle, and as far as like more poles are concerned, in this description, we have exchange of higher spin particles. And again, these higher spins are not usually what is observed in quantum field theory or in experiments, but from the string theory point of view, there are infinite tower of such massive higher spin exchanges. And that is one of the reasons why the string theory is so exotic, because of the presence of this infinite tower of massive high spin states. So now, again, going back to this function, here we can see that if we choose t to be negative, then this function can be entirely expanded in terms of poles in only one variable s. So if we look at the denominator closely, we have s minus n, and n, the sum runs from 0 to infinity. That means there are infinite set of poles in the S, and just by collecting terms and adding the pole terms in S variables, we can recreate the entire function. And this can be done only in the region t less than 0. And similarly, we can have another expansion where S is negative, and we will have an expansion in terms of the t channel poles. So this is an example of a function which can be expanded in terms of a single channel poles, and this was one motivation to look for such functions. And this this partially answers our question that we now have example of amplitudes which can be given as sum over poles either in the S channel or T channel. Now, what is not clear is that can we express this function as sum over poles in both S channel and T channel? And for a long time, the answer was not no. So we could write down a function which has single channel expansion, but not double channel expansion, which converges for all values of S and T. So now let me introduce dispersion relation. So dispersion relation is it's a byproduct of complex analysis. And using the dispersion relations, what we can do is basically we can reconstruct a complex function if we know enough about the singularity or analytic structure of that function. And that is why analytic structure of a complex function is so important. If we know the location of its poles and other singularities, we can actually construct the full function, provided we know something about its high energy or like large variable behavior. So it is very much like knowing about the constituents of white light. Like if we pass white light through a prism, it breaks into different colors. And using the dispersion relation also, the reason it is important in S matrix is that we can know about the constituent particles, like what are being exchanged and other things about the S matrix. So here, what we do is like we try to gather information about the singularity, or what is actually referred to as a discontinuity of the amplitude. For example, if we have a function like 1 by x, it has a discontinuity around x equal to 0, and this discontinuity is given by a delta function, Dirac delta function. And in other exotic examples, if we have some branch cards or logarithmic, for example, if we have log minus s, then s has a branch point starting from 0 all the way up to infinity. And if we cross that branch point, the discontinuity is basically 2 pi. So in that way, we can know about the discontinuity of an amplitude, and from the discontinuity, we can now reconstruct the full amplitude like this way. Now, there is always some domain of convergence for the dispersion relation to hold, or domain of validity. In usual cases, for example, if we choose the physical region, and physical region actually corresponds to S being positive, T negative. In that physical region, the amplitudes have certain high energy property. By high energy property, what we mean is that if we take S to infinity, okay, so how does the amplitude behave? And complex analysis tells us that when you deform, so this is basically about contour deformation. We start off with a function like that. So this has a pole around sigma equal to S. So we are doing an integration over the sigma plane. Now we are deforming the contour. So what it will do is it will pick up discontinuities from this function m of sigma t, and also there may be a contribution from the arc at infinity. And to like to relate this discontinuity, or the pole at sigma equal to s, with the discontinuities of the m, the amplitude, what we require is the arc of infinity to die. And this usually does not happen for ordinary quantum field theory amplitudes, but for the special amplitude that I showed in my previous slide, the string amplitude, this actually happens because the Euler beta function that we wrote down, that has this property s to the power t as s is taken to infinity. And now what you can see is that when t is negative, this actually decays, because this is going as s to the power minus some number. So as s goes to infinity, this actually decays, and therefore the arc contribution dies. And that is the reason why we can apply this dispersion relation, and this is usually referred to as fixed t dispersion relation. The reason is that we are holding t fixed and writing the full amplitude in terms of singularities over one single channel, which is S here. Now, this is usually not the case. Like ordinary quantum field theory amplitudes do not satisfy this fixed t dispersion relation unless like we use some modifications of that, which go by the name subtracted dispersion relations. Let us not go into the subtracted dispersion relations, but the take-home message will be string amplitudes, because of its certain high energy property, can be written using this fixed t dispersion relation as shown here. And this was all done to describe some phenomenological processes, to explain some scattering processes involving hadron scattering back in the days of 1960s or so on. And people thought that, yeah, because these hadron scattering, they have nice high energy property, one can come up with this dual resonance model, which satisfies the single channel expansions where fixed dispersion relations are applicable, and so on. And Dolan, Horn, and Smith, so they were actually postdocs with Murray Gell-Mann, and they were observing, or they were studying this hadron scattering, and they tried to explain the experimental observations of this high energy experimental data. And they use something called this finite energy sum rule. to explain this high energy pion scattering. And in contrast to the popular notion of the single chain expansion, what they noticed is that the single chain expansion uh, does not appropriately hold in the case of this hadron scattering, and one requires some modifications. Modifications in the sense that so these are, back in those days they were called the Rayleigh poles, the exchanges. Like, so there are two kinds of poles. One is this S channel pole, which are the direct poles, and then there are another poles or non-analytic structures in these T variables, and those are, for some reason, those are referred to as Rayleigh poles. So what they observe is that one can not only expand, I mean, one cannot directly expand in terms of the external poles, but also need to include the cross-channel poles, which are called the Rayleigh poles, and then there will be some kind of overcounting, which have to be compensated by removing some terms of this form. So, in a word, in a summary, to say what their results, their findings was that the single chain expansion could not be applied, and that requires some modification. That means fixed T dispersion relation does not hold in the case of this hadron scattering. And in fact, so string theory originated earlier as a study of, like, from the study of this QCD or hadron scattering. So, like, lot of history of string theory dates back to the study of this QCD scattering, and people were very much motivated from the study of this QCD or flux tubes, so on. And in that context, they proposed this dual resonance model. But the pioneers of string theory, so this is a famous book. This is like one of the oldest books in string theory, and the authors are the pioneers of string theory. The authors are Michael Green, John Schwartz, and Edward Wheaton. Like any, so these are very classic textbook, and any student of string theory starts their course in string theory reading this book. So, in fact, in the first chapter, the authors were also a bit skeptical about this dual resonance model. For example, this dual resonance model, they have a limited domain of validity in the S and T variables in the kinematic space. And the question that they asked is the following: is duality an approximation or a principle? Because whenever they try to explain the scattering in terms of this dual resonance model, they were assuming a lot of mathematical properties. But in reality, the question is whether this dual resonance model actually hold or not. And their thoughts can be reflected in this writing. They say that duality hypothesis never had more than slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis. So, like, it's a very beautiful, elegant mathematical study, but in reality, one may not find models like Veneziano model which satisfy these duality properties. And in fact, in last year, in the annual strings conference, so these are like annual meetings that keep happening. In the annual strings conference, people were told to write down set of questions that would be important for like next 10 years and so on. So David Koswar, who has worked on various things like QCD, gravitational scattering, and has been like an eminent personality in this field. And this is what he had to say, that string theory had its origin as a theory of hadrons. Since then, we have discovered there is an enormously rich structure of string theory as fundamental theory. But the utility of having string-like theory of hadrons to bridge the gap between perturbative QCD and low-energy expansion, such as chiral Lagrangians, would still be great. So basically, what he was alluding to is some kind of not rigorous string theory, but a string-like model that would still be able to describe the experimental findings. So it is an effective setup where we can apply the models of string theory. And this is what he says, that the required theory would be an effective string theory. By analogy with an effective Lagrangian, it would have a cutoff above which it loses its validity. So basically, So when we say infinite number of poles, that means there is an energy scale, and the energy scale goes all the way up to infinity. And in practice, it should go all the way up to 10 to the power 19 GeV, the Big Bang scale, something like the Planck scale. Now, like doing something, probing some physical phenomena at that energy scale is impossible. So we have access only to some limited energy scale. And like our motivation or the question is whether in the limited energy scale that we have, can we find some model that would approximate as string theory models. So instead of going all the way up to the full, up to writing down infinite number of terms in the S channel, can we have a setup where we keep still finite number of terms up to a given energy scale, and still can we say that this is a string like model in that uh, effective description. So that is the motivation, and in fact that's the question that we ask in our work. And with this motivation, so these are the objectives that we want to explore. So our question is, can we obtain a field theoretic representation of tree-level string amplitudes? And these representations should satisfy the following properties. One, where crossing symmetry is manifest. For example, when we expanded these Euler beta functions, we expanded only in terms of S channel. And the crossing symmetry was lost, because if we just go back to this expansion here, like if we just focus on this representation, this is not manifestly crossing symmetry, because this holds in a, first of all, this holds in a particular domain t less than 0. We have poles only in the S channels, but where are the poles in the T channel? So although this function to begin with was manifestly crossing symmetric, but this function is not. So there's a subtlety here, and we want to ask that, can we have a crossing symmetric, manifestly crossing symmetric representation of such string amplitudes, which we involve poles in both the channels, not only S channels, but S and T channels both. And except the physical singularities, amplitude should be analytic and convergent for all values of the kinematic variables. And then there are some regular terms in the representation which should also converge. And the regular terms we refer to as contact terms, meaning apart from the singularities, we will get some polynomial kind of terms. So those come from the contact terms. For example, if you have a FIFO theory, that vertex contributes to 1, and there's no pole or singularity associated to that. So those kind of terms should also emerge out from that representation. And importantly, for a certain range of kinematic variables, say SI refers to S and T, which is less than some energy scale R, the infinite series representation, if we can truncate that to retain reasonably finite number of terms, n of the order of that energy scale R, then the truncated representation or the truncated sum should exhibit important features of the actual representation. And that is the goal. So some kind of effective description that will hold in a particular energy scale, not all the way up to infinity. So again, to go back to the Euler beta function, in a summary, so this is the function that we have, and this is the world sheet description of this amplitude. So to say, we integrate over the z variables, we get this one. And already we noticed that for this integral to be valid, we require S1 and S2 to be negative. Otherwise, like this integration will diverge. And also we saw that this representation has a summation expansion of this form, either expansion in the S channel or T channel. And here I'm referring to S and T as S1 and S2 variables. That's just a change of variables. Now the question is, can we write this in a more manifestly crossing symmetric form? And in fact, attempts have been made in the literature, like even in this book, Grasham and Reisig. One can, by suitably changing the variables, one can rewrite this integration in this form, which looks slightly more crossing symmetric. And then if we expand, like if we do some Taylor series expansions around z equal to 0 and z equal to 1 and integrate term by term, we'll obtain this kind of representation. Now note that again, this converges only in a limited domain, that is real part of S1 and real part of S2 should be negative for the convergence. And just as I told, by performing Taylor series expansion around z equal to 0 and z equal to 1, we'll obtain a representation of this form. And this looks more crossing symmetry because this has poles in both S1 and S2 variables. Okay, but can we claim that this representation is more at par with the quantum field theory representation? The answer is no, because this representation has some very limited domain of convergence. In fact, this representation converges only for real part of S1 plus S2 greater than -1. Meaning, if we have S1 is equal to, let's say, -2 and S3 is equal to S2 is equal to -2, then this representation would not converge. So this is not in the spirit of quantum field theory representation. And therefore, this is not a very useful representation also. Okay, by the way, Jishnu, how much time do I have?
We are almost done, but you can take how long you want to finish it? How long it will take?
So can you give me another 15 minutes? Then I can try to wrap up. Is that possible?
Okay, can you? Maybe we can think of it. I think can you wrap it up in next 10 minutes would be nice, but
10 minutes,
you can
okay,
take
no problem.
You're free to extend it.
Okay. Yeah, let me summarize. I'll try to finish it then. So yeah, as I alluded to before that, although we can try to make these representations crossing symmetric, but like there will be some troubles, some problems regarding the limited domain of convergence and so on. And in the literature also, there have been other attempts to make this function more crossing symmetric. For example, Giddings used Wheaton's string field theory to make some crossing symmetric combinations like this. But again, this also does not hold because this has some non-local terms, as can be seen from these powers 2 to the power S1, 2 to the power S2. These are not quite field theoretic representation. Now, we have come up with a representation using something called crossing symmetric dispersion relation, which takes this form. So this is the representation of the Euler beta function. And let me just explain the notations here. So this big bracket with the subscript, this denotes Pochhammer. Pochhammer is basically some ratio of the gamma functions. Okay. So, and this will be a polynomial of order n. And as you can see that like there are poles in S1, poles in S2. There are infinite sums, n going from 0 to infinity, but it is manifestly crossing symmetric. And importantly, although we have a free parameter lambda here, after we sum over these infinite modes n 0 to infinity, the lambda dependence actually goes away. So on the left-hand side, we obtain something which is independent of lambda. And in fact, lambda has its own usefulness. Lambda is what enables us to connect to some field theory framework or Lagrangian description. And if we tune lambda, meaning if we take lambda to infinity, we will recover the summand of this form. And this is exactly what we encountered before in this representation obtained in Grasstein and Ricey. And in fact, if we choose lambda is equal to a certain value minus S2, then we will recover this representation. So lambda lets us play around with our representation and connects with the other different representations that we have. The question is, why is this useful? This is useful because, okay, so here's some numerical explanations why this is useful. So we have like tried different set of values for S1 and S2 to see how much these representations converge with the actual known answer, because known answer can be computed in computer. In Mathematica, if we just give this function and ask for values at particular values of S1, S2, it will give some answer. And then we can cross check how much, like keeping up to some terms. Let's say n is equal to some 25. Keeping 25 terms in the sum, how much do they converge? And what we see is that our new representation converges for any values of S1 and S2, whereas for other representations, for obvious reasons, they struggle to converge. Like if they converge for one particular values, they would not converge for the other particular values, like that. And okay, so I talked about Euler beta functions, but I talked about Euler beta functions, but a more realistic model is this open string amplitude. And the difference with this Euler beta function is this one. So earlier we did not have this one here in this denominator. And this actually describes something called gluon scattering, and it's a super partners and so on. And this representation also has a series represent. I mean, this function also has a series representation of this form, which is here, and this is also manifestly crossing symmetric. And some things like real part of lambda should be greater than -1 for the series to converge. And in fact, this series has a very fast convergence because of the fact that at large n, the summand grows as n to the power -2 minus lambda. And if we compute the residues, they will be independent of lambda. And the fact that this is important is because the residues give the information about exchanged particles. And we expect the exchange particles to be independent of any free parameter that we introduce. Okay. So the convergence is very high, and this is an added advantage. And so lambda basically implies that we have a Lagrangian description, and we can do field redefinition to that Lagrangian description. And if we do field redefinition, we know that intermediately the contact terms and other things, they change in the Lagrangian. But finally, the amplitude, like if we sum over all the modes in a scattering amplitude, the final answer should remain the same. Although at intermediate stage, because of field redefinition, we introduce some ambiguity, and lambda precisely captures that ambiguity. And whatever I wrote down, if we compute first few terms, this is what we will get. So these we call the exchanges. These are usual. For example, if we draw diagrams in phi cube theory, we will have some exchanges where there will be poles in S1 and S2 variables. And in addition to that, there will be some contact terms. And the contact terms are what depend on this lambda. Okay. And for particular reason, we need to choose the space. So D here refers to the space and dimension. For some reason, we have to choose D to be less than equal to 10 for the unitarity to be hold. And unitarity is an important property. And that's why people say that a string theory is defined in 10 dimension. So here we have gotten an expression of field theory, like a field theory expansion from our amplitudes. So although now the important point that I was making before is that if there is an energy scale, and if we truncate that sum, the amplitude should behave constantly with the truncation. And this is what is actually being referred. So here we have truncated the sum, and then we vary lambda, and we get almost a plateau. That means that even the truncated representation, in spite of having this lambda dependence, if we just compute, that behaves quite steadily with the variation of lambda. And this is what gives us the effective field theory picture. And this is what lets us connect with some kind of Lagrangian description. Okay, so I'll skip some slides, and let me say two things, one about zeta function and one about pi. So this representation that we have gotten here, like using this free parameter lambda, that allows us to like obtain some representations, like series representations of transcendental functions, which are called zeta functions. And zeta functions in mathematics is defined for integer values is defined like this: 1 over n to the power k, n running from 1 to infinity, this summation. And these are called zeta k. So now, by taking various low energy limits of the amplitudes, we find some new representations for zeta functions. For example, here is a new representation for zeta 2. Okay, notice the introduction of the free parameter lambda. And here, if we take lambda to 0, it will reduce to 1 sum over 1 by n square. Now, so we now have a parametric representation of the zeta functions, which converge faster than the original representation 1 by n square. This is not the fastest converging representation, but definitely faster than the usual original representation. And so here are some numerics thing, meaning we have also obtained new representation for zeta 3, which converges faster. And these are checked using computers. And like we obtain, just keeping some 25 terms in the summation, we can obtain a convergence for more than 15 decimal places. And we even have a generating function for the zeta functions like this. And so here, like this is a generating function, and if we want for any zeta j value, we can obtain using these Stirling numbers and Jacobi polynomials for the representation for the zeta functions. And finally, the thing that I want to talk about is we also have a new representation for pi. So this pi comes if we take this open string amplitude and put S1 equal to minus half, S2 equal to minus half in that representation. On the right hand side, we obtain a series of this form. And this gives a new representation, parametric representation for pi. And in fact, if we take lambda to infinity, we recover the old Madhava representation, Madhava-Leibniz representation for pi, which is given of this form. And in fact, this, needless to say that this is faster converging than the usual Madhava series. Like this above series, this one takes 5 billion terms for convergence to 10 decimal places, whereas this representation actually requires 30 terms for a range of lambda chosen between 10 and 100. So this is faster representation. And now, like, can we have a proof that given this representation, so for some time it took us some time to come up with proofs for this representation to be equal, like to say that this representation is equal to pi. There can be various derivations or proofs. So I'll just mention about two such proofs. One was by mathematician Halmer Rosengren. So he gave a derivation using partial fractions. And then a student, Shonak Pal from IIT Gandhinagar, so he also gave a proof using something called Sommerfeld-Watson transform. So Sommerfeld-Watson transform is using complex analysis. So what we do is we do analytic continuation of this function to the complex domain, replace n by any complex variable z, and then we look for poles. And then it becomes a problem in the complex analysis, like to find out discontinuities of this function. And this sum, meaning we have poles at z equal to various integer values along with a pole at z equal to 0. And in that way, and there is also a pole at z equal to minus lambda, but that pole actually cancels. One can show that. And that also proves the independence of lambda for this series representation. So this is a way to prove that this is indeed is equal to pi. And we obtained various things by a new kind of representation that I did not talk in detail. So this is newer than the fixed T dispersion relation. So earlier we had only this form. And then what we could introduce is a kind of new crossing-symmetric dispersion relation. And by tuning this lambda, we can go to various other dispersion relations. So this is a new kind of dispersion relations. For some reason, we call it like stringy dispersion relations because of the presence of this lambda parameter. So, okay, I'll probably stop here. I do not have much time to like explain things, but they are also not required. Sorry, Jishnu, you are muted.
Yeah.
Yes.
Yeah. So thank you, Arnab. So maybe now
Thank
let's leave the room for the questions. Do you have any particular questions? You can unmute yourself and ask. I hope all are allowed to unmute. There is no restriction from the host. Yeah, so you can unmute, and if there is any questions, you can ask. Okay. If there is no question, maybe I would take this time to thank Arnab. Arnab agreed in the first chance itself. We asked for, when we requested for the talk for KTPI. Thanks for your generosity. Thank you very much. And in
Thank you,
addition to that,
Venkat. Yeah.
I wish to ask a couple of questions. One is this single channel expansion. When you do,
Yes.
you're
Mhm.
always assuming the S and T are independent kinematical variables, right? So
True.
then
True.
when we say that there exists a single channel expansion, is it true that S and T are somehow related, or so,
So S and T are not related, meaning S and T are independent variables. But
so
when you
when
say
we
a
say S
single
and
channel
T,
expansion,
yeah. So then if one can one can so can we physically interpret it in such a way that if you know one kinematical variable, we will understand the amplitude,
no. For example, let's say this representation. Okay. So this
right?
representation
Right.
has this expansion. So here the pose
Yeah.
during the S1 is manifest. But now if you want to
Okay.
evaluate this function at some values of
Yeah.
S1 and S2, you have to supply both S1 and S2. So it is
Yeah.
not
So
true
the
that only knowing the value of S1, you can reconstruct the function. So what it
okay.
actually does is that we have an expansion in terms of the singularities in one variable, but we still require the other
Ah.
variable, the value of the other
Okay.
variable to evaluate that function. And in that way,
I see.
S1 and S2 will be independent.
I see. I see. Okay. 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 And at some point, I have seen that you're also analytically continuing these variables.
Right, right. That's very
The
important. Yeah.
so what does it physically do? Is it something related to the causality, causal structure
Right.
or something?
So yeah. So when you say analytic continuation is happening to go from the string world sheet to the actual
Okay.
physical amplitude. And in
Okay.
fact, and that's also a kind of limitation for the string theory that when we describe this amplitude on the string world sheet, here you see that
Mm-hmm.
S1 and S2 have to be necessarily negative. If they are not negative,
Mm-hmm.
let's say if they are positive, then you see that there are divergences coming from z equal to 0 and z equal to 1.
Okay.
And when we describe the processes in experiment, we want S1 to be
Mm-hmm.
positive and S2 to be negative. So that is
Okay.
the analytic continuation when you go from the string world sheet to the
Okay.
actual representation.
Okay.
But in our case, or like if we just say consider this function independent of itself, like independently, then we do not require any analytic continuation. So this
Okay.
function is actually
Okay.
defined for all values of S1, S2. There may be
Right.
some
I see.
poles, discrete poles.
Mm-hmm.
So
Mm-hmm.
analytic continuation is at the level of the string world sheet, but they have got nothing to do with the representation by itself. Or even in our case, we do not require to do any kind of analytic continuation.
Okay. And one more question. If there is no other question, if there
Yes.
are
Yeah,
there any question, please.
yeah, Jishnu.
Yeah.
Uh, s- Thank you for a wonderful presentation, first of all. And
Thanks.
my question is, um, why did you put S1 equal to and S1 and S2 1 by 2? Is there any reason? You just put it.
No. There was no particular reason. Just that, from here itself, it should be obvious. Think we just wanted to like equate with pi, meaning we know that gamma of half is square root of pi. So that is the reason when we substitute S1 equal to minus half, S2 equal to minus half, we get the left hand side to be pi. And that was the only motivation. Meaning it was a byproduct of the representation that we have. It is not the main result.
Okay, thank you.
So
Thank
that
you.
was just a choice that we made. Yeah.
Yeah.
Yes, please.
So I think someone is trying to speak. The Rajagopal Naik, are you speaking? So hello, we couldn't hear you if you are speaking. I can see that you are unmuted, but yeah, okay, thank you. So here, and Yeah, she unmuted. So one thing I want to ask is another question auxiliary to what I understood from your talk is that is there any stringy-like representation for QCD amplitude with this kind of representation? Like you're saying that the truncating the amplitude at some level and you will get an effective, not up to the infinite energy scale order, but you truncate up to certain order, like Planckian mass, Planckian energy order, and you could describe
Yeah,
by
not
an
that we know of, like
okay.
because whenever we describe on the string worldsheet, so they would involve this integration, and this integration will automatically come with this infinite sum.
Okay.
Like
okay.
So this
Okay.
truncation is probably not there in string theory, but in string field theory, probably
Okay.
one can make sense of this truncation. And string field theory is
Okay.
not something I'm quite familiar with. So people try to do field theory in the worldsheet setup, and they are so our representation is more in the spirit of the string field theory.
Okay. 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 So I think there's a question in the chat by Rajagopal Nair. Can you please write a bit more, because he was telling that his question was motivated by the equations in the slide 4 for ST, etc. So,
Right.
so what is the question? Can you write, or because we are unable to hear you? So I try to ask you to unmute. So maybe I can unmute. Is there anything I can do about it? So can you try speaking? So he was asking, they are due to the conservation of energy. However, there seems to be no classical analog. Is it true?
Oh, classical analog? No, I think even in classical processes, still it would be true. Because so far there is nothing quantum about these equations. We have used Lorentz invariance. Lorentz invariance will definitely be there in the classical analog, and momentum conservation will also be there. So this is this holds true both in classical as well as quantum setup.
Okay. Is there any other question? You can raise your hand or you can unmute yourself and ask. No problem. If not, we will conclude in a few minutes. Thank you all. So there will be another talk on June 14th by Yashi Tiwari. So we will announce it soon, and so you'll circulate among yourself. Thanks for being here, and Anurag, thank you so much for giving a wonderful talk. And there are more to understand. I hope, even though audience could not understand many of the details, but they will get at least a flavor of what is really happening in the frontier of these kind of researches.
Sure.
So thank you so much. We will end the meeting here. Thank you.
Thank you.